So let's start off with a couple of formulas here for common drag force functions. There are a lot of different mathematical functions that can be used to model a drag force on an object that's falling through air or a liquid of some kind. And two of them that are very common are basically the ones that are shown here. In the first case, you could have a force that says the drag force is equal to a constant times the instantaneous velocity of the falling object. In other words, the drag force is directly proportional to the speed of the object. If the object is falling at twice the speed, it has twice as much drag force. 3 times as much speed, 3 times as much drag force. This formula is actually oftentimes applied to low-speed objects, and it's sometimes called viscous drag. I'm not going to get into an explanation of why that is, but in many cases this works for objects that are moving at low speeds, like a baseball that you might kind of just throw, at a low speed. The second formula is called the high-speed drag formula, and it's very similar. It says that the drag force is proportional to a constant times the velocity squared. Okay, so c is just a constant, but notice that the exponent is different, and this actually means that the drag force is going to grow much faster as a function of velocity. So if an object doubles its speed, the drag force should be 4 times greater. If it triples its speed, the force should be 9 times greater. And this formula oftentimes works well for objects traveling at high speeds. Now, don't get too, attached to either one of these formulas, because in real life, oftentimes it's kind of in between. And when I say in between, what I actually mean is that the exponents don't have to be equal to 1 or 2. Sometimes that they can be things like, in between. It could be an exponent of 1.5 or 2.3. And it depends on a lot of things. So it's kind of complicated, which makes it interesting. In the derivations we're going to do today, I'm going to focus on the low speed case because that's probably slightly easier to present to you. In your homework, you're going to actually do the second case following the exact same steps. So I would say probably both of these drag forces are equally easy to work through and derive, but I'll show you the very first one. All right, so our goal is going to be to derive the velocity as a function of time and the acceleration as a function of time for an object that's falling through air. I'm going to sketch a free body diagram. And on the diagram, I'm going to label, of course, the weight, and I'm going to put the drag force up here, and I'm going to use the k times v drag force. So this is the first one, the low speed one. When I basically set up my coordinate system, then I'm going to make down positive and up negative, because that just makes my life simple, because this object is just going to be falling, and I want the falling direction to be positive so that I have the least amount of negatives to deal with. So what I'm going to do here is something I've never done before. We've never done this before. Is I'm going to start with Newton's second law, and then I'm going to write it in a different way, which gives us something called a differential equation. And then we're going to solve it, and the solution is going to be the velocity as a function of time. So let me write Newton's second law the usual way, which is that the net force on the object is equal to mass times acceleration. Okay, so that's the way that we usually start things off. And I'm going to write down my sum of my forces. I have mg, and then I'm going to subtract k times v, and that's going to be my my left-hand side. So far, kind of so good. So stuff we've done before. Well, here's where I'm going to do something different. I don't want to write acceleration in this term here. I don't want to write a, because I am looking for a solution which involves velocity. So instead of writing a, I'm going to write dv dt. In other words, I'm going to replace acceleration with its derivative with respect the velocity with respect to time. Okay, so this is something that kind of goes back to our early days in this class. And what I have now is something that's called a differential equation. Scary. Okay, we've never seen one of these before. And what's interesting about this is that the variable, so to speak, is v. Okay, we want to get v, but unlike other cases, v is not a number. We won't get a solution for v like v is equal to 5 or something like that. Instead, what we're going to get is a function. And so the solution is not a number. It is a function. In this case, the function v with respect to t. Okay, and that's quite different. And so we have to kind of look at this carefully and solve it in a slightly different way. Okay, so that's a big difference here. So this is a differential equation. Now, what we're going to do, the trickiest part of this whole problem is probably what I'm about to do next, and it may not be obvious to you as to why we're going to do this, but I'm going to do a substitution here. I'm going to substitute this. I'm going to basically take mass times gravity out of the differential equation, and I'm going to replace it with k times vt. Let me do that first, and then I'll explain exactly why. Okay, so the substitution would be k times vt minus k times v is equal to m dv dt. Okay, now what's the deal with that? The deal would be that if you wait for a long time, right, and you allow this object to fall for many seconds, what eventually is going to happen, let's say when I'll say when t is equal to infinity, but I just mean when t is equal to some long time, what's going to happen is that we know that the weight of the object will be perfectly canceled by the drag force. They should be canceled out. But we know that the drag force is equal to k times v. We also know that that velocity approaches a limiting value. So in the special case, where the object has been allowed to fall for a very long time, we can replace kv with kvt, and that vt is an actual number. That is a number. That's the top speed. And so these two vectors should cancel each other out. So that kvt should be equal to the weight. And so that's the substitution I'm going to do here. And I'm doing that, I guess the reason is because I want to get as many v's in my formula as I can. Please note that this v, this is just a number. It's not a function. So when we proceed with solving this, we are not going to treat that like a function. It's just going to be some type of a number. But it's convenient to use that instead of using mass times gravity. Okay, so let's go ahead and let's now take our formula here, our differential equation, and I'm going to divide both sides by the mass, and I'm also going to factor out the k. So if I factor out the k, let me start with that. If I factor out the k, it would look like that, right? Because k multiplies both terms. And if I divide by the mass, then I'm left with the derivative on the right side of the equation. Okay, so just some algebra there. The second thing I'm going to do is I'm going to take a negative out here. And again, just trust me on this one for now. I want to have this in the form of v minus vt. Okay. And so this is the form that we want to basically put the differential equation into. You want to have the derivative by itself, and then you want to have negative of constants out front, and the difference of the velocities in here. Now keep your eye on the function. Where is the function? The function is here. The function is here. Okay, and we need to get a solution for that function. And again, this vt is simply a number. Okay, so what we're going to do then is to actually use a technique called separation of variables. And I'm going to go to a different page here. So the way that you solve that equation is a technique called separating the variables. And we've kind of already separated them. But let me write it again. dv dt. All right, so I'm gonna write it. I'm gonna flip the two sides around. So my derivative is on the left side. My other stuff is on the right side. What we do when we separate the variables is we're going to now, in a sense, kind of cross-multiply the parts of the derivative. Okay, so derivatives can actually kind of be split up. And so what I mean by that is I can multiply both sides by dt. Okay, so I brought the dt over here by multiplying both sides, but I want to bring the stuff in parentheses over onto the left side because I want to group the velocity terms together. So if I divide both sides by those terms, I get that. Okay. Now, that's what it means to separate the variables. Separating, we've got the v's together, and the t is by itself. These constants do not have a t in them, but we usually put the constants with the t term. Now, the next step here is that we want to solve for our function for the velocity. This means we have to actually integrate both sides. All right, so we have to use calculus here to do this. We cannot solve this with algebra. So I'm going to put an integral sign out in front. And the integral sign here on the left side is going to be an integral with respect to velocity. And then I'm going to put an integral sign on the right side. And that integral is going to be with respect to time. Now notice I can take the negative k over m and I can just pull it outside because k, that's just a constant. And on the right side I end up with a very simple integral to do. Okay. So that's what we've done here. We've separated the variables. We've integrated both sides. What I'm next going to do is I'm going to put limits or endpoints on these integrals to make these definite integrals. And so we're going to go from a time of 0 to t. And so I know those aren't actual numbers. Well, 0 is a number, but t is just a variable. But you can do this. We're going to integrate from 0 to some time t. And over here, we're going to integrate from an initial velocity of 0 to some final velocity v. Now, that's not the terminal velocity. That's just going to be a variable. And we're going to act like that was just a number when we solve this. Okay, so let's solve this. This is the world's, let's do the right side first. This is the world's easiest integral to solve because you have k over m. The integral of dt is just t, and you evaluate it from 0 to t. So that basically comes out to be negative kt over m. So that's a super easy integral to do on that side. On the other side, we want to take the integral of this function, v minus vt, and I think I'm just going to write down the answer to it first and then justify it later. You've got basically 1 over v minus a constant. So the integral you should be thinking of here would be the integral that shows up for 1 over anything. In other words, the log integral. So we do ln of v minus vt. That has to be evaluated from 0 to v. Okay. We can talk more about that later, about why that is. But it's a substitution. Okay. And I'm just going to present it like this for now without showing the details of it. Okay. So it's just a substitution type of a thing. All right, so let's evaluate then the left side of this. That would be the natural log of v minus vt minus natural log of 0 minus vt. We have a difference of logs here, so a little bit of fun algebra. The difference of logs is the same thing as the log of the quotient. Yes, you have to know that stuff. Remember, there's a negative sign that pops up in the second term. That's got to come downstairs. And this is equal to negative kt over m. Okay. We're almost there. We just want to now isolate and solve for that function. Remember, that's the thing we're keeping our eye on. We want to get a solution to that. So how do I do that? I've got a log function here. I'm going to exponentiate both sides. I'm going to raise each side to the e, or take the e and raise it to each side. So it's kind of like putting an e here. That's my exponent. I put an e here. That's my exponent. These expressions should be equal to each other if the arguments are equal to each other. And of course, the value of doing that is that e to the natural log just becomes the argument. Okay, like so. And we're almost done. Now we just have to kind of get the vt over here. So v minus vt gives us that. And I need to add vt to both sides to eliminate it over on the left side here. And we're almost done. The last step here would be to factor out terminal velocity. And that gives me this expression. That expression is in fact what I was trying to get. I have now a function for the velocity with respect to time. So the time is built into the exponential. There is a negative exponential going on here that has a constant in it. And vt is just a number. And so it's going to be vt times 1 minus a negative exponential. All right. So what does that actually look like if you graph it? Well, if you have a negative exponential, in general, if you have e to the negative, let's say y is equal to e to the negative x, that's going to look like this. Okay. Now that's not what this function is here. This is going to be 1 minus that function. And so what this is going to look like is going to be kind of have the opposite shape, where this is your velocity, this is time, and this limiting value here is the terminal velocity. Okay. So the thing that multiplies out in front, this constant right here, becomes the asymptote of that function. And then the function starts at 0 and it approaches that asymptote. And you should know probably from math class that 1 minus a negative exponential is going to give you a function that looks like this. So in fact, we've got a function here that does make sense. It matches up with our prediction. It approaches a terminal velocity. What else? The velocity starts at 0. It ends at a terminal velocity after a long time has gone by. There's a few other things in here that we can talk about in a minute, but for now, let me just say mission accomplished. We have our velocity. All right, so I'm going to stop it here.